Everyone can hear me okay, hopefully. It's exciting to be here. At Idaho National Laboratory, we build nuclear reactors. We build and test nuclear reactors. There are 16 advanced reactors in development right now. There are 92 light water reactors in operation in the United States. They produce 20% of your electricity. Little did you know. And almost all the codes that are used for the verification, validation, compliance are run in our data center. And believe it or not, they're all using MVAPICH. So that's why we're here. The Idaho National Laboratory, the codes for nuclear fuel performance, neutronics, diffusion, thermal hydraulics are all based on the Moose framework using MVAPICH 2. And so we've worked closely with Hari and DK for many years as these codes are used for maintaining the current light water reactor fleet, as well as developing the advanced reactors that you're seeing coming online. There's been a lot of news. You'll see a lot of stuff about nuclear reactors and HPC centers recently. A lot of kind of the future of nuclear energy. A lot of the nuclear energy industry developers, vendors, they work closely with us. And one of the things they see HPC data centers as an end user for nuclear power and a substantial growth area for them in the coming years. That's just one example. It came out in March where the Amazon Web Services acquired a nuclear data center that's sitting right next to a pressurized water reactor in Pennsylvania. Now, believe it or not, there are currently, there's only 12 here, but there's actually 13 microreactor projects underway that specifically call out HPC data centers as their end users. So they'll be calling you at some point. These are just some of them. Now, microreactors are kind of it's a new class of nuclear reactor. They're small, they're modular, and they have refueling cycles, and instead of like 18 months, they go for 10 years. They're autonomous. There's no one controlling them, but they're also kind of quirky. A little challenging to work with currently. But these are just some of them. They generally produce power in the order of, say a megawatt to maybe up to 15 megawatts. But they're uninterruptible power sources for 10 years. It's kind of an exciting development as these come along. Let's see which is the laser pointer. They may be mobile. They do have a load follow limitation, so that has a significant impact on HPC systems and people running codes. And Marvel is the one that we're building at Idaho National Laboratory right now. I'll show you some pictures and some of our studies for that. Okay, so this is the Marvel microreactor. It's a SNAP 10A design. It flew in space in the 60s, a SNAP 10A. It's got 4 Stirling engines on it. Let's see which is the... Okay, well, maybe that's not it. Okay, it's got 4 Stirling engines. It's really small. It fits in our treat facility. It's going to only produce about 50 kilowatts electric, so it's not a lot of power. But we have access to it, and we can hook up our HPC systems to it. And so we can actually power HPC off the microreactor and do some experiments. So that's been really neat. And those experiments are using MVAPICH. So this will be ready in 2026, but it's kind of a neat facility. This is where the computer science advances that are made here are actually being placed into practice across the United States and in advanced reactor technology. The Natrium reactor being built out in Wyoming. It's a fast-cooled sodium reactor. Another one that's the simulations are happening using the Moose framework, which is based on MVAPICH too. Another one, the Vinci microreactor. This is one that's going to be, this Westinghouse is developing it. It's a 5 megawatt electric. It does produce a lot of heat, so you can't put it quite underground yet, but it fits in a semi-truck. It's really small. We'll run for more than 8 years without having to refuel it, and it's autonomous. So it's kind of a neat design, and that one is specifically targeting HPC operation. This is our mobile data center. We actually have it on a trailer so we can drive it out to the desert and hook it up to the reactors and run tests. We have just 3 compute racks, and we run a lot of simulations with MVAPICH 2 and our neutron diffuser or our thermal hydraulics codes in this container when we hook it up to things. Okay, so this talk is about butterfly valves, though. And you say, what is a butterfly valve? I guess these are just some of the modeling and simulation cases for the Marvel microreactor. It's a sodium potassium cooled reactor. Laser point, I guess, is not working. But essentially, we have these, the Stirling engines at the bottom, we have a coolant coming up that's recirculating in a loop, and we monitor the thermal hydraulics for the microreactor using the flow. Basically, we do everything in simulation as the system's being built. So HPC, I guess I should mention a little bit about the data center that I run. So we support about 1,800 users. Every single company doing every startup company doing nuclear energy runs on our systems. Everyone in the United States, most people in Europe, Japan, Canada, anyone doing nuclear regulatory work runs on our systems. We supply currently about 160,000 cores. The nuclear energy industry is generally risk averse, so most of the codes are just CPU based. They don't adopt to good. They haven't really moved to heterogeneous computing just because it takes so long to validate these codes. We've got another big system, so we run both OPA. We also run InfiniBand. We've got lots of a wide variety of systems, and we have to make sure everything is validated and working for all these codes across multiple different networks and architectures. And our systems run at about 96% utilization with the average size at about 1,000 cores. Okay, so this is a butterfly valve. This talks about butterfly valves. Every single light water reactor has about 1,500 valves in it. That's the most crucial component of a nuclear reactor. There's a lot of valves. A butterfly valve, well, that's actually one right there. That's a really big one. It's about 1 meter across. It's essentially, it's a design to be able to, for running really high Reynolds numbers, high flows, to minimize the pressure difference across the valve. That's why you have butterfly valves. And they can rotate open or rotate close. They're really fundamental for maintaining, in terms of a reactor. This is the advanced test reactor out at in the desert at Idaho National Lab. It's using both. It's a pressurized water reactor in the sense that it uses both water as the neutron moderator and as the coolant. A lot of your isotopes used for cancer treatment are made out here. This facility. It's kind of a neat facility. And this is the butterfly valve from that facility. Now, one of the goals of Idaho National Laboratory, a lot of these codes that we're developing for developing nuclear reactors are intended to become open source. Some of them are already. And so it's exciting. We want to kind of open up these codes. And as you'll discover, they don't perform terribly fast. Performance is a lot of work that has to be done in terms of getting these codes to perform better. But they do give the right answer. So we can at least say that. So this is a butterfly valve. This is the most common simulation for every single light water reactor. You're going to be computing failure rates, the torque on the butterfly valve. It's a really important simulation, commonly done, and we're doing it, in this case, with an open source framework, which is kind of unusual. Most time it's done with closed source stuff that you can't really see. You can either do it with star CCM. These are some results, looking at the velocity of the fluid across the butterfly valve. Okay. So I should mention the Moose framework. So the Moose framework is developed I'm not a developer on it, but it's developed in the same building. We sit in the same offices. It's an open source multi-physics simulation environment. It can do neutronics, it can do thermal hydraulics. You could probably do cancer dosimetry on patients too with it. It's a really cool code. It really does some neat stuff. It is entirely built off MVAPICH 2. All our containers we ship, we use MVAPICH 2. So we've worked closely with Hari for a long time. So we find bugs and fix things and get this. But if you try MVAPICH at home, if you try Moose at home, you'll discover it doesn't run as fast as probably it could. If you were to take Shamir's code and start running some tracing on it, you discover we could do a lot better in terms of performance. And that's just because the focus has been on getting the physics right. You don't want a bad answer, so it really is good at that. 100% open source, easy to learn, well documented. But for us, the most important piece is it has to be easily containerized. It has to run on lots of different supercomputers at scale. So like we might ship out a container to Southern Electric. They run quite a few nuclear reactors. And they're going to run that code, but it's got to work. And it's got to run on 1,000 cores or 2,000 cores. Not terribly large scales, but they're going to run a lot of them. So it has to be really easily containerizable. And it has to work on, say, well, maybe the customer has OPA. Or maybe the customer has InfiniBand, or maybe it's got to work across a large number of supercomputers and give the right answer always. Now, one of the main goals was to make simulations easy to reproduce. And so the Moose workshop, they actually they'll have their workshop in March, kind of going through the state of the art for Moose. And of course, the growing application we're seeing for Moose is medical. A lot more interest in kind of looking at dosimetry cases, simulating Moose. So that's what I used for this simulation. Now, this is work done with my colleague Daniel Juncker and I. So Moose, the idea is that everything should be open source. You should be able to do the nuclear reactor simulations, or in this case, the butterfly valve simulation, entirely open source. Meshing was performed using Qubit. Now, one drawback is Moose does require conformal meshes. Well, so that's kind of a nasty restriction, but it makes it so your meshes have to be cleaner. Here's the results. So this is for the actual ATR reactor at Idaho National Laboratory. On the left is the pressure and velocity profile for different angles. We see these eddies that you expect to form as the valve opens, and then the velocity streamlines on the right. So these simulations, typically you could spend thousands of hours getting just this result. What's more interesting, you say, well, that's quite a bit, right? But go ahead. You may want to speak into the microphone so they can hear you online.
What do the two bars for each figure indicate, like the top bar and the bottom bar?
Yeah. So on the far right, the legend.
No, like the top and the bottom, like horizontal bars. What do those visualizations indicate? Like these two, the horizontal. Yeah.
So this is the velocity. This is the pressure difference.
Okay.
So the idea is a butterfly valve minimizes pressure difference across the valve. You've got these holes in there. Now, what's really fun is when the butterfly valve breaks, right? That's when it gets exciting, because it's going to flip around, right? It's completely unstable when you're running these high Reynolds numbers through it. And that's a severe problem. The other thing is we have mechanical valves that actually control, there's a mechanical torque system that controls this valve. And so when that snaps, it causes all sorts of problems. And so most of these types of simulations are determining what happens when the valve fails. That's the more interesting case. And in nuclear energy, we call those transient cases. We like to break the reactor any way we can and every way we can, as many ways as we can, prior to actually building a thing. Well, in this case, this is one that's actually built. Most light water reactors in the United States are quite old, 40, 50 plus years. And so the idea of being able to say, well, how many years is this butterfly valve going to be able to stay in operation? Understanding the torque and essentially the torque on the butterfly valve as it operates is one of those numbers that we use for determining the predictive maintenance on the system. Okay, so thousands to tens of thousands of hours to do a simulation like this, and everybody has to do them. And you have to do them fairly regularly. So that's quite a bit of simulating power that's going directly towards supporting the sustainability of the light water reactor fleet. And that's why we're really concerned. We're more concerned about performance right now. This is something that's really coming up. And so you'll see more, we're really excited about seeing ways we can improve Moose performance even better to be able to make these simulations a lot faster. I think we even did a proposal last year on this. Couple months ago. Obviously, the simulation isn't any good unless it matches reality. So here's for slow and fast inlet speeds. Essentially, we do 3 resolutions. We always do 3 resolutions. And the comparison with the experimental, the red line. So essentially, we can exactly match or very closely match to second-order convergence, pressure drop, resistance coefficient, and flow coefficient for each of these valve angles. And this tells us something about torque. We can actually compute these numbers into torque on the valve and get some ideas about the predictive maintenance for the valve in the reactor. So again, 1,500 valves, 92 reactors. You do the math. There's quite a few simulations that have to be done just to maintain a nuclear energy facility operating. Okay. What are some challenges? So it's a neat case. There's a paper coming out on it just exploring an open source framework doing this type of work. These are the Moose Herd apps that are currently out there. They are, some of them are going open source very shortly. But for the most nuclear energy operators don't get the source code for this right now. They just get the executable, and then they run it, they get it in some sort of a container. Bison handles all of the fuel performance, fuel burn up rates, change out rates, those sort of things that you compute. Griffin, that's the neutron diffusion solver, heavily used, and that's the one that has medical applications as well. If you want to do dosimetry for cancer treatment or something. And then the Sabertooth. That's a really cool code that combines it's the fuel performance. It's kind of a combination. It's fuel performance, it's thermal hydraulics, the behavior of the coolant, and the neutron diffusion all at the same time. So I'll just talk about one of them, Griffin. So what are the issues we see principally? The Moose sparse communication routines, which are built on MVAPICH 2, not very good. We could talk a little more about this, but the key thing is this does actually directly impact performance. And so we suspect that Griffin probably runs about 100 times slower than what it should. That's how bad. So massive opportunity. Now imagine, think about it there, okay? I've got 92 reactors, and then we've got 16 advanced reactors in development right now, and all of them are using this, and everyone's running code that runs 100 times slower than what it should. Okay, so you can see the scale of the problem, which is why I'm here. I can't give you a solution, but I can at least tell you that is a problem that exists, and we'd love some of you bright graduate students to solve it for us. Anyways, these are kind of some of the Moose herd apps that are in development. They've all are all qualified and verified. They're kind of really neat codes, and looking forward to many of them being open source. And Griffin's probably the earliest one to be open source. So neat opportunity there. Okay, so what are the challenges that we see? Again, I apologize. This is kind of an application-specific type talk here. Nuclear energy modeling and simulation. So if you're going to build a reactor, you care about transients. You're going to be doing a lot of simulations. And the code that you use has to be extensively verified and validated. So DK talked about 18,000 hours of core hours per commit. I think we're 10 times that. I mean, we really hit these codes hard in terms of verification and validation because it has to be right. Most of the people using these applications are not computer scientists. Okay, they're nuclear engineers. They get a code. They're running on their, Southern's supercomputer, or maybe they're running on our supercomputers to get simulation results. And so we have to support a wide variety of networks, okay, OPA, InfiniBand, anything, lots. We have to always get the exact same answer. We have to be 100% reliable in terms of being able to operate, like running containers and large numbers of cores, 1,000 cores, maybe 10,000 cores. One thing we'd really like is long-term guidelines. We're supporting MVAPICH with containers on host with InfiniBand and OPA, and provide a unified container that works for hosts with different fabrics. Right now, we provide different containers for supercomputers with different fabrics. So those are some of the challenges that we see looking forward for the impact on the nuclear energy industry. And it's exciting to think about, one other tangential impact. It's exciting to think about the fact that nuclear microreactors will be coming. If you work in the supercomputing field, you're going to get a call from somebody at some point trying to sell you a microreactor that's, that's about $140 per kilowatt hour, and they will run for 10 years, but they won't have very much load follow. And so when you run your application, well, it's the positive swing that will kill you, right? The positive swing on the load follow. All right, so that is my talk. I can open it up for questions.
Let's thank Matt. So do we have questions? So, yes, Amir.
Do you use GPUs?
Okay, so we do not use GPUs for any of these codes. And the reason why is the nuclear energy industry is very risk averse. And that's probably a good thing. So they will not, these codes have a lifespan in some cases 20 years. And there is an effort underway to move some of the codes to GPUs, but it will probably be 4+ years out. And just at the level of verification and validation that has to occur. So at this point, there are no GPUs in the entire nuclear energy software stack. There's no using GPUs.
And it's using PETC internally?
It is using PETC internally. That is correct.
And do you support the Grace architecture, like Grace, or
So we have started experiments on Grace. It's not officially supported in our container suite, but it will be. And that's in the near term.
okay? Thank you.
I have one question. So you mentioned that the applications were running, I think Griffin you mentioned, was running probably 100 times slower.
Yes.
So could you give us some idea about where the time is being spent? Is it in communication, computation?
The sparse communication routines are terrible.
So what sort of sparse communication is it using? What primitives particularly? Is it like point-to-point? Are you trying to use neighborhood collectives or collectives?
The collectives are bad.
Okay.
That's always the case.
Okay.
But the point-to-point communication, they have a significant time overlapping communication.